Okay. Today's special guest is Snap, as in Snap, Crackle, and Pop, and his mother, Squeak. And over here on the other side, running away, come back. Oh, he's gone now. You'll meet him later. Is his brother, Crackle. Oh, there's Snap again. I wanted to name him Kiss because of that makeup job and hairdo, but I was overruled. Hello, Squeak. These guys are currently available for adoption through Tiny Paws Rabbit Rescue, in case you've been interested in having an adorable pet bunny. All right, what we're actually going to cover today, though, is our week 3 lecture on hypothesis testing. All right, so last week we covered descriptive statistics, wherein we were just describing the data as it exists. Today we'll start talking about hypothesis testing, which is the first part of inferential statistics. So where we try to use a sample in order to infer or learn something about a population. So because it's impossible to sample the entire population, right? Usually there's just too many people for us to get to them all, and that's way too expensive. We just select a few of them, and we hope that they are representative of the population as a whole. So our ability to make the inference is determined through what's known as hypothesis testing, or its full name, null hypothesis significance testing. So what we're trying to do with this is we're trying to come up with the idea of whether our results are because of what is actually happening in the population, or if what we're seeing is because of sampling error. So did it just happen randomly or by chance, or is it something that actually occurs? If you'll remember, we talked about how in order to be generalizable, we need our sample to be as representative as possible of the entire population. So what we try to do is random sampling of the entire population. Again, usually not possible completely though, because people self-select to take part in studies, but we still check to make sure things like the racial distribution of our participants matches that of the wider population and similar things. On the other hand, as you'll remember, random assignment, that's where we have our sample and then we randomly split them into groups, thus trying to control for that sampling error. So the first part of hypothesis testing involves generalizing about populations, right? So the larger the sample size, the more able we are to make those generalizations. For example, if we know that a particular social work treatment protocol is successful over 70% of the time, we can generalize to individual clients saying that there's a probability of 0.7 that it will be successful for them. Probability basically means the certainty that something is going to occur. A probability of 1 means that it is certain that something is going to occur. Probability of 0 is almost certain that something is not going to occur. The larger the sample size, the smaller the probability that what we're seeing is just due to random chance. What probability really does for inferential statistics, it tells us that the differences between groups can be attributed to chance or a real effect. And it can also tell us whether the attributes of a sample are reflective of the population as a whole, given some margin of error. And this margin of error is determined by confidence intervals, which I'll talk about in a second. Before we talk about confidence intervals, though, we need to talk about theoretical sampling distributions. Now, that sounds scary and complicated, but it's not. The first word in that name really lets you know that this is something that does not exist in the real world. It's completely theoretical, completely mathematical, and you will never need to calculate it. SPSS and similar programs will do it for you. So what a theoretical sampling distribution does is, say you're trying to figure out the best average for a sample of people, it will take a small number of people from your sample, calculate an average for them. Then I'll randomly select another set of people, calculate an average for them, repeating that basically an infinite number of times until all possible groupings have had their averages calculated. And when you plot all of those averages, you will get usually a normal distribution. The larger the size of the sample that you are drawing from, the more likely your theoretical sampling distribution is going to be a normal distribution, like that bell curve that we talked about last week, because of this thing called the central limit theorem. So basically what the central limit theorem tells us is the larger the size of the sample, the more that the average or other attribute we're trying to calculate is closer to what is actually happening within the population. And most of the inferential statistics that we're going to talk about require a normal distribution. Those are what's known as parametric statistics. They're called parametric because they require certain parameters to be met in order to use them. And one of those is normal sampling distribution. So that's why we try to increase our sample sizes as much as possible so we can decrease our sampling error and get to that normal distributions. So these theoretical sampling distributions are actually used to estimate our likely degree of sampling error. And sampling error is just that error that we get through our sample and how that sample might differ from the actual population that we are drawing from. We do that. Come on, switch sides. We do that by calculating the standard error. So no matter how large the sample that we're able to gather, there will always be sampling error. And it's influenced by size because of the way that it is calculated. So the standard error is the standard deviation of the theoretical sampling distribution, right? How an average has a standard deviation, so does the theoretical sampling distribution. It has a standard error. And the way it's calculated is you take the standard deviation and you divide it by the square root of the number of samples that you have. That's why the larger the sample size, the smaller the standard error is going to be, because that sample size is here in the denominator. And the bigger it becomes, the smaller that standard error is going to be. Now, you don't actually have to calculate this again. It will always be provided for you. You just need to be able to recognize what it is when you see it. So standard error, standard deviation of the theoretical sampling distribution. Standard deviation is when it comes to averages. It's for the actual distribution, not the theoretical sampling distribution. So what we get from this standard error is the ability to reduce the dispersion in the theoretical sampling distribution so that our estimates are more precise. So what it allows us to do is calculate these confidence intervals. So we can say with 95% certainty, for instance, that the true value of a statistic is within this range. Again, you won't need to calculate this for this class. They'll all be calculated for you. But with 95% confidence interval, we can say for certain that there's a 95% chance that this is the true value and only a 5% chance that we are incorrect. All right, so let's look at the actual steps in hypothesis testing. The first step is to come up with a research hypothesis and then break it down into a null hypothesis and an alternate hypothesis. And this is why it's called null hypothesis significance testing. We're always testing that null hypothesis. Null meaning nothing is happening. So that's why usually it's worded as there is no effect of this on this. For example, there is no relationship between anxiety about statistics and a student's grade on a statistics test. The alternate hypothesis is always going to be that there is an effect. So there is a relationship between one's anxiety levels and how well one does on a statistics test. We then conduct the statistical tests, and we look at the resulting p-value and check whether it's below a certain predetermined cut point. The p-value is the significance level, or the probability of being wrong. The most frequently used cut point is 0.05. So we set our cutoff at 0.05. We're willing to be wrong 5% of the time. If our statistical test has a p-value that is less than 0.05, that's what's represented here by this, p less than 0.05, we can reject the null hypothesis and conclude that there is an effect. If not, then we haven't really proven that there is no effect. All we have done is failed to reject the null hypothesis. I mean, the effect might still be there. We just can't find it. It could be that sample size is too small, or that the effect itself is just quite small. The significance value, so not only is it the probability or chance of being wrong, it's the probability of conducting what is known as a type 1 error. So type 1 error is where we conclude that an intervention is working when in fact it's really not. So by putting that p-value at 0.05 means that 95% of the time we're pretty sure that the intervention is effective, and 5% of the time we are could be making an error in that judgment. So this is again where that probability comes in. P stands for probability. So P is equal to 0.05. 0.05 probability of being wrong, or 5% chance of being wrong. Now, there's two types of hypothesis questions that you can come up with. There's the two-tailed, which I just gave you an example of, right? There is an effect or there is no effect. It could be a positive effect, it could be a negative effect. We are leaving that part open. When that happens, the rejection region is divided on either side of our sampling distribution. So if our intervention is very effective, it could be somewhere in here, or if it's very ineffective, we could have statistical value somewhere in here from our statistics tests. With the one-tailed hypothesis, we specifically specify a direction. So we say our intervention will have a positive effect, in which case we are looking for a value here on this side. Now what this does is it gives us 5% chance here, all crowded around this one tail, instead of dividing it between two tails, because if you divide 5%, you're going to end up with 2.5% here and 2.5% here. So it's harder with a two-tailed or non-directional hypothesis test to achieve a positive result. However, problem with this is that you're more likely to make a type 1 error. You really should not be using a one-tailed test unless you have a really, really good reason. Like, for instance, there's a ton of literature that says that, yes, your intervention is definitely going to be effective, because if it turns out that your intervention is actually harmful, you're going to end up missing that. Because with the one-tailed test, you can only look at the either positive effects or negative effects at a time. You can't look at both. So best to stick always with the two-tailed hypothesis and don't specify a direction. So you're not increasing that type 1 error or the chance of being wrong. Besides type 1 error, which is represented by alpha, which is incorrectly rejecting the null hypothesis. You believe there is an effect when none exists. There's also what's known as type 2 error, and it's represented by the Greek letter beta. And that's where you fail to reject the null hypothesis. So you believe there's no effect when one actually exists, otherwise known as a false negative. There's a trade-off between the two of them. If you if you decrease alpha, so make it less likely that you're going to make a type 1 error, you actually end up increasing the type 2 error because you're being more conservative. We typically set type 1 error, or alpha, at what I mentioned, 0.05 as our cutoff, and type 2 error we typically set as 0.2 as our cutoff. So we're willing to fail to reject our null hypothesis 20% of the time. Here's a cute little graphic to help you remember it. So when it's a type 2 error, it's that false negative. You are looking for a cat and you see a dog, and that type 1 error. When you're looking for a dog, you end up seeing a cat. What you can do to decrease the risk of a type 2 error is to increase your sample size, because when you increase your sample size, you increase the statistical power of the test. And statistical power is literally the probability of 1 minus whatever you set your type 2 error at, which again usually is set to 0.2. And the reason type 2 error and power are so connected is because that's how power is calculated. It's 1 minus that beta, or 0.2. So power is the ability to find an effect if one actually exists. So if, as I mentioned, we do what most people do and set our beta at 0.2, then our power is equal to 1 minus 0.2, which is 0.8, or we have an 80% chance of finding an effect if one genuinely exists. Power is very much influenced by the size of the effect. A bigger effect is easier to find than a smaller effect. You will see in social work, in most therapies, that effects are quite small and take a long time to materialize, especially for hard to treat conditions such as anxiety, depression, things like CBT, cognitive behavioral therapy, etc. They will have small effects at reducing symptomatology over time, but that's why they're harder to find, because the size of that effect is smaller than we would like. That's why we can increase the sample size. So big sample sizes mean more power because there's less standard error. Remember how standard error is calculated with that sample size as the denominator? And lastly, if we're less strict about deciding when an effect is significant, we're more likely to find it. So we can change that alpha to something larger like 0.1, if we're willing to be wrong about the effectiveness of our intervention 10% of the time, then our beta increases. You don't have to calculate how much power your test has. There is software available to help you calculate it, and that is called G-Power, and we will be working with that in a few weeks when we start talking about actual inferential statistical tests. There's a few important caveats to remember about hypothesis testing. So the first one is that a significant result doesn't actually mean that the effect is important. It just means that it exists. And then at the same time, a non-significant result doesn't actually mean that the null hypothesis is true. We could be wrong, right? We still have that type 2 error that we encounter about 20% of the time. At the same time, a significant result does not mean that the null hypothesis is false, because we've got the type 1 error, right? 5% of the time we are wrong. And then there's what's known as p-hacking. And p-hacking is where people will try multiple analyses and report only the ones that yield significant results. It's a type of data mining, and you'll see some unscrupulous researchers doing that. Instead of starting with a logical hypothesis and testing only that, they test everything they can and then report only the things that are significant. And then there's what's known as harking, which is hypothesizing after the results are known. So you present a hypothesis as if it was made before the results were known. And that harking and p-hacking really go hand in hand as a way of manipulating statistical results and lying with statistics. So back to that effect size, right? So the effect size we talked about before, it is the actual size of an effect. We will be calculating it for each of our statistical tests. And it's a way of measuring the size of an observed effect relative to background error. There's different values that allow you to compare across studies. So this is why instead of just looking at the p-value, we always look at the size of the effect instead. Why do we look at the size of the effect? Why is the effect size much more informative than the p-value? Because it's not influenced by sample size. So the bigger your sample, the more likely you are to find a significant effect, but doesn't tell you anything about the size of that effect. The effect size, when calculating it, is not influenced by sample size. Therefore, you can actually judge between studies whether the effect is meaningful, whether it actually tells you something about the population that you are examining. And the best way of actually doing that is through what is known as meta-analyses. So these are studies that combine the effect sizes from many, many studies that test the same hypothesis. These are some of the effect sizes that we'll talk about this semester. I know it's a lot. I just wanted to present you with one slide where you have all of them so that you can always be able to interpret based on what SPSS gives you. Is it a small, medium, or large effect? So you don't need to know all these. This is just a resource you can use when reading and interpreting the research literature. So when we talk about effect size, we are trying to address that gap within hypothesis testing, because hypothesis testing is really all or nothing. It's not judging whether there's any practical significance, and that's what we want to look for, right? An effect that is meaningful. So that's what substantive significance means that there's meaningful or practical significance of the results. So, for instance, cognitive behavioral therapy is not just improving people's anxiety by 1 or 2 points on an anxiety scale, it's actually improving their functioning in their day-to-day lives. Clinical significance, on the other hand, looks at how many people actually benefited from the intervention, right? So interventions are not going to be equally effective for all people. So clinical significance is usually reported as number needed to treat or number needed to intervene with, and it's especially for clinical trials, medications, things like that. But basically, how many people do you need to administer the intervention to before you see, a certain portion of them actually being recovering from whatever it is that ailed them. We, in social work, mainly focus on that substantive significance as opposed to the clinical significance. And as I mentioned, meta-analyses are where you take all of these smaller studies and you conduct some advanced statistics on them in order to actually combine the results of multiple studies. Each individual study is going to have its own issues with sampling error, etc. So when you do a systematic review of all the studies that exist and you combine them together, you're able to actually show a trend towards efficacy, and they are the sort of top of the research methodology. They're at the top of the best practice scale. The only problem with them is that they're very, very time consuming and they cost a lot of money. The good news is, though, that there are several nonprofit organizations that promote, maintain, and disseminate these systematic reviews. There's the Cochrane Foundation that you might have heard of, which specializes on medical interventions. And then there's the Campbell Collaboration, which publishes a lot of systematic and meta-analysis reviews on social interventions. They're basically the gold standard of reviews. And they do that by gathering all the available knowledge about a particular social intervention and basically integrating it and presenting the findings for free on their websites. So I strongly urge you to check out these websites.